Let's talk about continuity. We've learned that for a function to be continuous at a certain point, then three conditions must be met. For one, the limit from the left-hand side as x approaches a from the left, a little bit less, of this function has to equal b. So let's see. Here's our point as x gets closer and closer and closer to a from the left. So we're squeezing in on a from this side. It does look like the y values are going to b. So we've met the first condition. The limit as x approaches a from the right, so we're squeezing in on a, is also b. So as we squeeze in on a from this side, yep, it does look like the y values are heading towards b. And the function value at a is b. And we see if we put an a into our function, we do get b. So all three of those conditions are met, and we can say the function is continuous at a. What would be an example where we wouldn't have a continuous function? Well, what if I put a open dot here and then said this point is up there? Maybe it's a piecewise or multi-rule function. So now the limit as we squeeze in on x from the lesser side, from the left side, the function is heading towards b. The trend in y is b. So that's true. And the limit as x approaches a from the positive side, or the right-hand limit, is also b because our values are trending towards b. However, f of a looks like it's c if we put this value c up here. The y value itself is c. So this wouldn't be continuous even though our first two conditions had been met. So that's not a continuous function. Remember what I said is that if we don't have continuity, then we have to pick up our pencil. If we're drawing this from left to right, I'd have to pick up my pencil at the hole. So it's not continuous. How about another example of a non-continuous function? Well, one would be something that looked like this. Maybe I have a graph that looks like this. And you can see that the limit from x approaches a from the left-hand side is still going towards b. But, let me bring this c down just a little bit now. But the limit as x approaches a from the positive side, from the right-hand side rather, y is heading towards c. So already we know we're not continuous. And maybe I put the actual value here. Oh no, we have the value there. And then f of a is c. But these don't line up because the limit from the left-hand side is going towards b here. So that's not a continuous function at a. The last case, or a third case we can consider, is when we have a vertical asymptote. And maybe we get something that looks like this. Our graph goes down, 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 and up, up, up. And so the limit as x approaches a from the left, as we squeeze in on a, y is heading towards negative infinity. As we squeeze in on a from the right-hand side, y is heading up to positive infinity. And the function value at a does not exist. For a function to be continuous at this point, x equals a, these all have to agree like they did in the first case. So you can see this fails on multiple levels to be a continuous function. Let's classify the types of discontinuity we were just talking about. We can have whole or point discontinuity. This is the only removable discontinuity. Look at the limit from the left, it's b. The limit from the right is b. But the actual point is missing. So the function value at a does not exist. We could change it and say, oh, well, here the function, the point is up here. We'd still have this whole discontinuity if I put that point in or not. If I don't put the point in, we say that the function value does not exist. The left-hand limit is equal to the right-hand limit, but f of a is not equal to whatever the left-hand, right-hand limits are. So we have a whole discontinuity. Jump discontinuity. Well, very simple. The left-hand limit does not equal the right-hand limit. And our y values are jumping. We'll have something like this. Now, this could be opened or closed there. We do have a function, but the function is discontinuous. Why do I say it's a function? It does pass the vertical line test. And that jump discontinuity is non-removable. Remember, the only removable discontinuity is the point. Notice the difference between these two. Students are getting these confused. If the trains are going into different stations, The y values are jumping, so we call this jump discontinuity. If the trains are going to the same station, meaning the limit exists here as x approaches a from two sides, it's b. The limit does not exist here. And finally, infinite discontinuity is also non-removable. That's found at a vertical asymptote. So our y values are going up to positive infinity from the right-hand side and negative infinity from the left-hand side. Just a thought here. The limit as x approaches a from the left is equal to the limit as x approaches a from the right. Both of those are equal to b because that's the trend in y. The limit as x approaches a from the left does not equal the limit as x approaches a from the right here. That's the difference between a jump discontinuity and a hole. The limit exists with the hole. It doesn't exist with jump discontinuity. And here, of course, the limit as x approaches a from the left is going to negative infinity. And here, the limit as x approaches a from the right is going to positive infinity. That was just a bonus review of limits.